Now this illustration deals with alternating current systems to be grounded. In accordance with 250.20 A, B, C, D, an informational note. I'd also recommend that you review 250.26 on page approximately 141 in the NEC that deals with the grounded conductor to be grounded. Now, those two kind of work together. Now, notice in the illustration to the left, you have a 120 volt winding, and we could choose either one of those legs, L1 or L2, to be grounded, but we chose in this illustration to ground the L2 leg, and that would not be a neutral. It could be used as a neutral, but it's considered a grounded conductor. Now we have the imbalanced current that could flow to the neutral in the drawing next to it. Then we have a 240 volt winding. We center tap, and it's 120 volt from L1 and L2 to the neutral, but 240 volt L1 to L2. The drawing below it could be 277 480. It could be 120 208, but notice the XO in the center is defined in Article 100 for XO. We tap there, and that's our grounded conductor and neutral conductor in this case. And we read from L1, L2, and L3 to the grounded leg there, 120 or 277, whatever the voltage may be. But phase to phase, it's 480 or 208, depending on the voltage of the system. And then down below the Y-connected transformer, we pick up a delta-connected transformer, and we're picking up 240 volt from L1 to L2 and L3, but the center tap of the 240 volt windings you see there, we pick up 240 volt from L1 to L2, but 120 volts from L1 and L3 to the grounded conductor, and then L2 above it is our high leg that we would look at. We would take 120 volts plus 240 volt, divide by the square root of 3, and that's where the 208 volt comes from. And then, of course, next to it is a corner grounded transformer, and that corner grounded transformer is phase to phase voltage. No grounded neutral could be involved at all. Now, when we really look at 250.20A, those systems are less than 50 volts. B to that section is 50 to 1,000 volts. C is over 1,000 volts, and D is impedance grounding, and that's 250.36 and 250.187 for less than 1,000 volts or over 1,000 volts. And basically, the neutral could, or the grounded conductor, maybe it's a better word, could be used as a neutral or a bonding jumper, plus a path for the fault current to travel over in accordance with 220.61, 250.102C1, and as well as 250.24D, and that's what this illustration is illustrating to the user of the NEC. Now this illustration deals with main bonding jumper and system bonding jumper in accordance with NEC 250.28C. And the purpose of the change, a provision was provided to point out that whatever means is used to serve as a bonding jumper means has to be suitable for the purpose. That's basically what this rule change and revision was all about. Now, notice at the note 1, the bonding jumper, it could be a screw, a strap, a wire, a bus bar, any suitable means that would serve as a bonding conductor. And then, of course, note 2 says basically that it has to be suitable for the enclosure so corrosion and stuff wouldn't set in and crystallize the connection and create a problem. And in 3, we have helpful sections to help us along and learn other important information. And you see call-outs in the black text that will help you do this. Now, depending on how you terminate the bonding jumper, Note 4 suggests that you look at 250.8, 250.10, and 250.12 respectively. And that's what this illustration is illustrating to the user of the NEC. Now this illustration deals with grounding electrode system and grounding electrode conductor. And it's just a revision to clarify that there's maybe more than one section you need to review to get this rule down, pat. Now notice the note explains everything. A multi-wire branch circuit is considered 1, 2, or 3 ungrounded conductors with one neutral. As outlined in Article 100, it's defined as such, and 250.32a exception works hand in hand with 250.30a exception to state that you can run this multi-wire branch circuit out to this detached garage, and you don't have to provide a grounding electrode conductor there. You can use the equipment ground off that 20 amp breaker there, which would be number 12, to ground and bond the light in the switch back to the earth ground at the service equipment located at the dwelling unit. And that's all this illustration is illustrating to the user of the NEC. Now this illustration deals with conductors in parallel, but we're dealing mainly with the grounded conductor, and in accordance with 250.30A3B. Now the purpose of the change was to recognize if you had a transformer involved, the parallel hookup still would be the same as you see in this illustration. 3 3/0 in each raceway, then 310.10 requires you to have at least a 1/0. But make note that a neutral conductor, if you calculated it by 220.61, and the neutral calculation was 2/0, then you would raise from 1/0 to 2/0. Or you would size it maybe larger than 1/0 in accordance with table 250.102C1, where these ungrounded phase conductors would be larger than 3/0. And that's all this illustration is illustrating to the user of the code. But be sure you read all of the blue typing, and it will say this very same thing that I'm saying to you. I'm just paraphrasing instead of reading each one of these individually. Now this illustration deals with grounded systems in accordance with 250.32B1, exceptions 1 and 2. Now the purpose of the change mainly is just to let the user of the code know that you use the larger of the calculated neutral load per 220.61 or the equipment grounding size from table 250.122 based upon the size of the overcurrent device. So for example, you have a 225 amp main, and say you had 4 conductors feeding this panel board. First you ground the service, and say it's to structural steel or metal water pipe. 250.32E would basically say that you would need a number 2 based upon the 4/0. Then you'd calculate the neutral load, and in step 1 and 2 we've done that, and it came up to number 6. But 225, the size of the main, per table 250.122 would require a number 4. So the size in the solution would be number 4 and not number 6 based upon table 250.122 and not the calculated neutral load per 220.61. But now make note of this. If the neutral was calculated to be a 1/0, then the neutral calculation would be greater than the number 4 from table 250.122, so you'd use the 1/0, and that's what this illustration is illustrating to you. But to get a handle on it, review the 3 notes, and it will tell you more detail what I'm just telling you, paraphrasing what the revision is all about and the purpose of change. And that's what this illustration is illustrating to the user of the NEC. Now this illustration deals with enclosures with ventilation openings in accordance with NEC 250.64G. And basically this revision just prohibits conductors, as you see in the illustration, routed across these vent openings. And the reason for that, you know why. The vents, top and bottom, basically pulls in cool air, and the cooler air takes the heat away from the windings through another vented opening. And that is basically what this rule is all about, is just don't cover up the vents so the transformer could overheat due to the loading of the facility that it serves. And that's what this illustration is illustrating. Now this illustration deals with size of alternating current grounding electrode conductor. In accordance with NEC 250.66, as well as Table 250.66 and Section 250.66A through C. But now let's just look at the purpose of change, and it was just a revision to let you know that the bonding jumper, if it's a conductor, would be the same size as the grounding electrode conductor. Now, when it's sized. So let's look at that. Look at the grounding electrode conductor sizing, where it's connected to the metal water pipe. Now, we would go over to Table 250.66 on page 149, and if we had 4 alt conductors terminating in a 225 main in that panel board, then it would need to be number 2. But if we went over and reviewed Table 250.102C1 on page 152, then this grounded conductor you see on the panel board and the system bonding jumper that you see on the panel board would also have to be number 2, as outlined in Table 250.102C1. And that's what this illustration is illustrating to the user of the code. But additionally now, if you connected the grounding electrode conductor to a driven rod, 250.66A, to a concrete encased electrode, it'd be number 4. To a ground ring, it would be at least number 2. And then if you want to really go into a good case study, look at the code change loop. The grounding conductor, you have your sections. The grounding electrode conductor, there are your sections. The grounding electrode itself, the system, then you have that list, all the sections listed. And then the system supply side bonding jumper, you have those sections listed. Can't go wrong. But this is a wonderful case study when you're grounding the service. So what is this telling you? Well, if I look inside that service and our 4 alt conductors hitting that 225 amp main, everything in that panel board, grounding conductor, a system bonding jumper, the bonding jumper, the grounding electrode conductor, if connected to a metal water pipe or structural steel, has to be number 2. The only difference in size, if you exceeded 1100 kc mil feeding that breaker, and you connected to a driven rod, concrete encased electrode, or a ground ring, then that conductor could be smaller than the other conductors we just talked about. And that's what this illustration really is illustrating. Now this illustration deals with the grounding electrode conductor connections. And the purpose of the change, the code panel accepted this revision to clarify that the terminating connection of the grounding electrode conductor has to be within 5 feet where it enters the building. Now that's the main point of view that this illustration is pointing out to the user of the code. Your point of entry, 250.68C1, and then notice if it's 10 feet or more of it in the earth, metal water pipe, and you are an electrode, and then you would terminate it within that 5-foot boundary, and that's what this illustration is illustrating to you in blue text and then black text to give you additional information. Now this illustration deals with other means. In accordance with 250.94B1 and B2, the purpose of the change was basically a revision that was accepted and added by Code Manual 5 to clarify the use of the larger per 250.94A. Now, let's look at Note 1. Note 1 says use the larger of the grounding electrode conductor, in this case is number 2, in accordance with 250.94A. But be sure you review 250.94A4. That's important too, to determine what this rule is all about. Now note too, it says the use of an IBT can reduce electrical noise, say we had communications type systems. And note 3 says make sure the connections are suitable for the connections being made. So the minimum size naturally is number 6 when you look at 250.94A4. So along with now 250.94A. But before you make such a grounding connection, make sure that you check with the authority having jurisdiction and review and listen to their interpretation of this new rule. Now this illustration deals with the size of the supply side bonding jumper in accordance with 250.102C1 and C2. The purpose of this change was that the code panel accepted a revision to clarify the procedure for sizing the supply side system bonding jumper. Now, notice in the panel board to the right, we have the system bonding jumper and the grounded conductor coming in. Now, reviewing the black text, a 4-alt is the ungrounded supply conductors, and based upon 4-alt, we move to the grounded conductor having to be at least number 2 per table 250.102C1 with the supply side bonding jumper has to be the same size. It has to be a number 2. But now moving to the left, we have 3 alts in parallel, and then a coordinates with 310.10G as well as 250.102C1 and 2, along with table 250.102C1, based upon it being a parallel hookup, then 1 alt is used for each one of those conduits to bond it into the grounded bar. Now down at the very bottom, we have of the illustration, we have 3 conduits entering from the bottom, and they have 3 alt conductors also in each raceway, and we're using 1 conductor to series all of those to ground. So we go to Table 8, Chapter 9, and a 3-alt is basically, it has 167,800 circular mil. Times 3 conductors, we'd come up with 183,420. And that would require from Table 8 to Chapter 9 on page 725 of your code book, a 4-alt to connect those 3 conduits to ground. However, if you were using individual conductors from each one, it'd be a 1-alt, just like in the illustration with a parallel hookup above, and that's what this illustration is illustrating. But now be sure, check out the grounding loop if you want to have a little case study and learn more about this subject in greater detail. Now this illustration deals with the size of a Wiretap equipment grounded conductor pulled in a raceway or raceways. Now the purpose of change is a lot of text there for you to read, and I'm just going to paraphrase it. It basically states that the code panel accepted this revision to clarify that an equipment ground in one raceway is sized off of the overcurrent device, and the equipment ground is pulled in that one raceway. But if you had parallel, then based upon the overcurrent device, the equipment ground is pulled in each raceway. Now that's basically what the purpose of change is relating. So just to go through this in a paraphrased procedure, the panel to the left, we have a 150 amp overcurrent device, and according to table 250.122 on page 158 approximately of your code book, you would need a number 6 grounding or equipment grounding conductor pull through that raceway. Now to the right, you have a parallel hookup, and you can't take 3 conductors in parallel and divide by 3 to size that the equipment grounding conductor. So they're saying you have an 800 amp main, so you have to take the 1 alt and pull it in each raceway. you cannot take the 1/0 and divide it by 3 and pull that circular mill rating in each raceway, then combine it and add it up. And that's what your 3 bullets or 2 bullets are relating to the user of the NEC, and that's what this revision is pointing out to the user of the NEC. This illustration deals with the size of a wire-type equipment grounding conductor pulled in a raceway in accordance with 250.122A. Now, there's a lot of text written in the purpose of change to illustrate and the procedure that would be used if you were routing an equipment grounding 1 conduit or 2 or more conduits, as you see in the illustration to the right. But let's just talk about the one to the left. If you should have a 150 amp main, what size equipment ground would you pull in that raceway? Then it would naturally be a number 6 by table 250.122 on page 158 approximately of the NEC. But the panel board to the right now has 3 conduits in parallel, conductors in parallel, terminated to an 800 amp main, so table 250.122 would require a 1/0 pulled in each raceway, not a 1/0 divided by 3 and then use a circular mill rating after dividing by 3. You wouldn't want to do that. They wanted to make that clear. And then just read your note 1, and it says that the equipment ground shall comply with 250.485 or B4 and selected in 250.118 where you're pulling it in a raceway where it's non-metallic or metallic, and then 250.134 item 1. The note 2 just says that the equipment grounding conductor never has to be larger than the ungrounded conductors, but must always meet the requirements of 250.122A in the table. So that's what this illustration is illustrating to the user of the NEC. Now, this illustration deals with increase in size, basically the equipment grounding conductor, in accordance with 250.122B, an exception. Now, you can see the purpose of change has a lot of text, but I'm just going to discuss with you the problem here that we were having. They were taking the equipment ground, and if you say the equipment ground was routed through an ambient temperature greater than 86 degrees Fahrenheit, they derated for that. If, for example, if it was a continuous type rated type load, they would derate for that. Correction factors for too many current carrying conductors in a raceway, they would derate. And basically, what they wanted the folks to do. Now, you think about it. If I derated for correction factors, adjustment factors, and 125% rule, I would have conductors that were sized, especially if I had a voltage drop problem, conductors so large you couldn't even terminate them. And electricians would saw the strands of the conductors. They saw out strands so it would fit under a lug, which was illegal, so it was just a problem. So the code panel, and paraphrasing this, they just wanted the electricians to know, and designers, that it was just due to voltage drop that you should increase it. And, if you needed to increase from a 2-volt to a 3-volt for voltage drop reasons, then that would be permissible. And so that's what these bullets is pointing out to you. But bullet 1 says you should be qualified if you're going to increase the equipment grounding conductor based upon voltage drop, where you increase the ungrounded conductors. And then note 2 says, hey, for similar under engineering supervisions, according to the sections listed, the equipment grounding conductor could be increased, and maybe it didn't need to be increased. So that's what this illustration is all about, and that's what the bullets 1 and 2 is reflecting to you, along with the additional information in the black text is giving you more information. So that's what this illustration is illustrating to the user of the NEC. Now, this illustration deals with the replacement of non-grounding type receptacles and snap switches when you have a branch circuit extension in accordance with NEC 250.130C1 through C6. And the purpose of the change, as far as I could tell, you're just including these switches along with receptacles that has been allowed in previous editions of the code. But now notice you have a panel board here to the left. You have a circuit right up there without an equipment ground. So they're just allowing that switch to be connected to a metal water pipe, just like they used to allow a receptacle. And if you look at these switches and receptacles over to the right, same thing. You can connect them to any water pipe system that extends out of the ground and is in the ground, where it's grounded and has a low resistance and so forth. And they're just allowing you to take these replacement switches and ground those in the same manner as we've grounded, say, a receptacle in existing editions of the NEC. And of course, this is all in accordance with 250.130, and that's what this illustration is illustrating to the user of the NEC. Now, this illustration deals with the continuity of an equipment grounding conductors and attachment in boxes. And of course, this is all in accordance with 250.148, exception A through D. The purpose of the change was just to ensure that all bonding jumpers, metal raceways, metal boxes, and equipment grounds were bonded together to create an effective ground fault path in accordance with 250.4A5. Now, notice to the left we have a receptacle, so the non-grounding type. But if you had an equipment ground, it would still have to bond that metal box. And then, of course, if you had a metal strap, means would have to be provided to bond that in, like with metal screws, in most cases there, that would bond that into the plate if it was metal to metal. And you'd look at that, I believe, in 250.146A, if I'm not mistaken. It's either 250.146 or 250.145 that we find those rules. Now, to the right, we have a grounding type receptacle. So the bonding jumper is connected as an equipment ground. It's connected to ground. We have a pigtail there that binds the box and the receptacle together. And then again, that bonds in the yoke, see? So we have that bonded in good. And that's basically what this illustration is illustrating to the user of the NEC. And I think the note 1 says it all. Equipment grounds and bonding jumpers shall be sized based upon the largest overcurrent device protecting the circuit. So looking at this box, if you had a 15 amp overcurrent device, number 14 would be your equipment ground size by 250.122 table. And if you had a 20 amp overcurrent device, it would be number 12. And that's what notes 1 and 2 is illustrating to you. In fact, that's what this whole illustration is illustrating to you, is to make sure you provide an effective ground fault path by bonding the equipment grounding conductors, the equipment ground metal boxes, and metal conduit together to provide such path.